All right, uh, let's get back to the discussion of MOSFETs. So in the previous video, we derived an expression for the current in a MOSFET. Let's try to get a typical number for a MOSFET. Okay. While doing that, I want to introduce what is known as a long channel MOSFET. When I say long channel, typically I could say that channel length is more than 1 micron. Okay. These were the traditional devices which were used in the 80s and early 90s. But after that, the technology has developed so much that the channel length became less than 1 micron. And when that happens, there are a lot of other short channel effects that come into picture that we will be discussing in the next week. Okay. Right now, when I say long channel, take the approximate channel length to be 1 micron. Okay. So that we don't have to worry. If you get to a small channel, then there are a lot of other effects. All right, let's see what happens with, this is a problem. I believe it, I've taken it from the textbook. I'm not very sure, but anyway. So the parameters of an N-channel MOSFET are given as mobility, which is 650 centimeter square per volt second. Tox is given to you, W by L is given to you, Vt is given to you. If the transistor is biased in saturation regime, what is the drain current for VGS equal to 1.2 volts? Okay, so well, this is a straightforward problem, but I just chose it to highlight a few points. One is, what is the mobility that we remember from the early discussions in the first couple of weeks? The mobility of NMOS was, I think, 1350 centimeter square per volt second. Whereas the mobility now given is 650 centimeter square per volt second. Why is that happening? Well, it turns out that it is an interface phenomena. The mobility in the bulk is still 1350 centimeters square per volt second. That's the most commonly agreed value. But when we come to the surface, we are dealing with an interface between silicon and silicon dioxide. So whenever you have such an interface, there will be scattering with the interface traps. They are few in number. Silicon dioxide interface is very, very good. But even then we have some scattering, and because of that, there is some degradation of the mobility. Okay, that's why the mobility will be smaller. Interface mobility will be smaller. Surface mobility will be smaller than the bulk mobility. Okay, that is one point that it's going to come back. We are going to tell you how it influences the drain current and all that later. So let's try to solve this problem. So what is the drain current? We said drain current was mu Cox W by L VGS minus VT. Well, it's in the saturation regime, so let's make our life simpler. Let's take this to be 2L and VGS minus VT whole square. Remember, whenever it's in saturation, we derive this expression. Okay, so this will be simply plug and chug 650 centimeter square per volt second into Cox. What is Cox? Well, yeah, that could be, we did it for the MOS caps. This will be epsilon oxide divided by thickness of the oxide. This will be 3.9 into 8.85 to 10 power minus 14 divided by Tox is 8 nanometers. So 8 into 10 power minus 7 centimeters. Okay. So I can calculate this. Well, I can say that 3.9 is approximately equal to 4. So 4 divided by 8, so 2. So that will be approximately equal to 4.4 into 10 power minus 7 farad per centimeter square. Okay. Yeah, that should be the 440 nanofarads per centimeter square. That's a typical number. Okay. So what will this be now? So this will be 440 to 10 power minus 9. W by L is 12. This is divided by 2 into VGS. My VGS is 1.2 divided minus 0.4 whole square. Well, this is the limit of what I can calculate approximately, I think. Let's see. So 650 into 440 into 6 into 0.8 whole square. Okay, there's a big 10 power minus 9 here. Well, it will be 6 into 4, which is 30. 6 into 4, 24 into 6. Well, when you calculate, it will be something in the range of, let's say, 100 to or hundreds of microamps to milliamps, something in that range. Okay, you'll just substitute and check this out. Okay, I'm not very sure how much is the number, and there's no point in me exactly taking a calculator and trying to do it. Okay, yeah. So this is a typical number for a MOSFET, and I told you that I'll show you the exact drain current calculated for a CMOS technology. This is basically what we refer to as 0.25 micron CMOS technology. I'll explain that when I discuss scaling more. And the device width was 10 microns, the length was 0.25 microns. And if you have such a device, you see that as your gate voltage is changing, this is VDS versus ID. As the gate voltage is increasing, the drain current is increasing quadratically. Okay. And the drain current is going from 0 to 600 microns here. Microns. You see that there's a reasonable amount of change in the current. So this is what, whenever we turn on the MOSFET, we have large current. When VG is less than, VT, then it is zero current. So that's how MOSFET acts like a switch. Simultaneously, you also see that at particular VG SAT or VD SAT for each gate voltage, you have a quadratic increase in the drain current. Okay. So this is for an NMOS device. So far, we never really discussed much about the PMOS device, but it turns out that the PMOS characteristics are also complementary. The only difference is that the mobility of PMOS devices is much smaller. So the currents will be smaller in the PMOS devices. Okay. Because remember, mu for NMOS was something like 1350 centimeter square per volt second, where mu n, mu p was, I think it was 400 or 350 centimeter square per volt second. So this is a bulk mobility. When you come to surface, it will be even smaller. Okay, so the PMOS currents will be smaller. So how do we deal with it? How do we increase the current in a PMOS device? Since mobility is smaller, typically we take the PMOS transistor to be wider. The W we take it to be larger to get the same currents. Okay. So this we have already seen the quadratic variation in the current. Okay. When you go to PMOS devices, we have exactly complementary situation. In an NMOS device, the electrons are entering into the drain because VD is positive, electrons will enter into the drain. So by convention, we take the drain current ID, basically means is positive when current flows out. Okay, flows out of terminal. When you take a PMOS device, you have holes which are moving and they flow into the drain. Okay, so here current flows into drain, and that's why we take it to be negative. The convention for current is negative now, and also VDS, VGS, VT, all of them will be negative. Okay, so basically flip the signs of VGS, VDS, and VT are reversed. Okay, that's usually the typical, well-designed PMOS device, which will be complementary to the NMOS device. That's why your drain current will be in this fashion, quadratically increases in the negative direction as VGS increases. This would be VG equal to 0. This will be VGS equal to, let's say, minus VDD. So as you go to minus voltages, it increases. Okay. So this is how the PMOS device behave. It's exactly complementary. So, so far what we have seen is, the drain, the parameters of the current, right, expression are fixed. Like for example, mobility, the capacitance, they are all dependent on the process. W by L is fixed by the designer. When you are fabricating the chip, you can fix it. So if you want to change the current, we have seen that VDS can be changed and VGS can be changed by the user. That is what we have so far. But it turns out that user has another way to change the current in a transistor, and that is by using what is known as body effect. Okay. So when I introduced the MOSFET in the beginning, I said that you have these four terminals, and we said that the body is grounded for NMOS transistor. For a PMOS transistor, it is at the supply voltage, VDD. But it need not be the case. We can actually change the voltage at the bulk or body. This is VB, VD is drain voltage, VS is grounded typically, and this is VG. So far we have seen that you can control this, but VB doesn't appear in our current expression, right? So current expression is simply current is function of VGS and VDS as far as the user is concerned. Does VB appear? Well, it actually does, but indirectly. The reason is, let's try to recollect how the current flows between the source and the drain. The current flows because, there is a barrier. Okay. Let me go back. The energy band picture. Let me say I have a constant Fermi level. And then I have a N-type source, N-type drain, and then I have a P-type channel. Because of that, I have a band which is forming like this. This is the band diagram, right? We showed it when we discussed the subthreshold drain. So we said that the electrons experience a barrier at both the source junction and the drain junction. So they cannot enter into the channel. But what happens when you increase VG? Well, as VG increases, the barrier is reduced and you can have currents which are flowing into the channel. Okay, that's how the current flows. We have seen the quantitative way of deriving the expression, but qualitatively we are essentially lowering the barrier in the channel by increasing the gate voltage. Okay, we saw that as you give a positive voltage to the gate, the bands move down, right? That's why the barrier reduces. Now, let's say I use my bulk voltage and actually apply negative bias to the bulk. Okay, what happens if I reverse bias this junction? Okay, I'll apply a negative voltage. That means I'm essentially going to reverse bias source bulk junction. SB or junction. So source is N plus and B is P. So that I reverse bias. So I apply negative voltage. What will happen when you apply a reverse bias? The bands move up, right? So when you reverse bias, source channel barrier becomes larger. Source channel barrier increases. When the barrier increases, gate has to work harder, right? So VT increases so that we get the same level of current flow. So in a way, by using my fourth terminal, which is a bulk voltage, if I apply a negative voltage for a NMOS transistor so that I reverse bias my source bulk junction, then I'll increase the barrier for the electrons, and because of that the VT has to be larger. Okay, and this effect is known as body effect. Okay, so if you look at the VT versus, I'll say, V minus VBS I'll plot. Okay, negative of VBS I'm plotting. So as I increase more and more negative voltage into the bulk, it becomes that much harder for the gate, to turn on. Okay, so VT increases. So you'll have a curve which looks like this. Typically, I mean, it need not be exactly a straight line, but more or less. So this is your, if for a 0.25 micron technology, 0.25 CMOS technology, this will be about 0.4 volts. And this might be, something like, this is, let's say, VDD, 2.5, minus 2.5 volts if I apply. It might become something like 0.5, not 0.5, 0.85. So I can effectively increase, double my VT. It is possible to do that. Okay. So this effect is known as body effect, wherein I'm changing the threshold voltage of a MOSFET by applying a voltage to the bulk. And the way to calculate that would be, there is a expression for that. I will not derive it or prove it. I'll simply give you the expression, which is going to be like this. So this particular term is known as body effect parameter. It has a units of 1 over root V. Okay, that will be given to you by the technology company. So what it tells you is that you have the surface potential, which we know, right, at threshold, which is 2πf. If you apply negative voltage, well, this first term is going to be larger than the second term. So that's why the threshold voltage increases. Okay. So this is a simple way of trying to capture that. Okay. I said it's not linear because this VBS is coming in the square root, but we don't really change it that much. So yeah, we can calculate the threshold voltage at a particular body bias. Okay. You might ask, what happens if I forward bias my source bulk junction? Well, if you forward bias it, you're going to reduce the barrier and the transistor action will be lost. That's why we don't really forward bias the bulk source or bulk drain junctions. That is avoidable. Okay, that should be avoided. So that's why typically in MOSFETs, we ground the bulk for an NMOS device, so that if I apply whatever positive voltage, I'm going to reverse bias it. It will never go into the forward bias. Similarly, for a PMOS device, I'll tie it up to the supply voltage, so that if I apply any other voltage, it will not go into the forward bias. It will always remain in reverse bias. Okay. So this is how some the transistor currents can be changed. So to summarize, the main tools that we have are, as a user, we can change the drain voltage, gate voltage, or the bulk voltage, all of them with respect to the source, and we can calculate. So if you have a body effect, well, the VT changes. If body effect was, body voltage was 0, then you have VT naught, which is the default VT, or it can change depending on the body effect. Okay. So with that, I would like to stop this discussion here today. And in the next lecture, we will talk about some performance metrics, or what are the different ways of evaluating a MOSFET, and we'll go forward from there. Okay. We'll also discuss things like subthreshold slope and all that, which are very, very important. So I'll see you in the next lecture. Till then, have a good night. Bye.